We were on time warp.
That has happened before. We're on standard now.
Yeah.
Okay, I'm going to review something, a really simple algebra technique that all of you have learned but probably haven't used recently that we will be using in every one of these problems. And this hopefully feels very familiar. I would like to solve this simple two-variable problem. Now, we know there are exactly 6 ways algebraically to solve this. One of them would be graphing, which is the worst way because if you don't have small integer answers, you can't see it on a graph. But we could use a matrix. We could do the inverse of the matrix. We can do addition. We can do substitution. We can do all that. So let's do this using the addition method, right? That's where I cancel things by addition. So if I multiply the top one, let's say, by C, and then what would I multiply the bottom one by? A. By A?
Negative A, yeah.
Actually, let's do the top one. Let's do the bottom one by positive A, and let's do the top one by negative C. That might actually be easier. Okay? Both sides. And then what I get is negative ACX, negative BCY, I'll keep everything in alphabetical order, equals CE, and then positive ACX plus ADY equals AF. And now when I add them, boom, I have AD minus BCY equals, so that should be a negative side. And then I have AF minus CE. So therefore, y equals, now as scary as this looks, this is either going to be a simple fraction or an integer, right? We already know that because I have integer coefficients. But that's the form of the answer. Now we do the same thing for x, to solve for the x's, I should say. And now I want to cancel the y's. So in order to cancel the y's, let's multiply, let's multiply this one by d, and let's multiply this one by negative b. Okay, doing the exact same thing. So now I have ADX plus ABY equals DE. I have negative BCX plus or minus BD. BD. No, that's not right. Hold on. Oh, this should be BD, shouldn't it? I can't. That's what I'm saying. I can't see this. This should be BD minus BDY. I would do this, but minus in the way, and that's minus BF. Does that look right? Okay. So now I have AD minus BC x equals DE minus BF. So x equals. Now one of the things, if I was teaching a remedial algebra course, I would tell them, whenever you're solving a system like this, you always get the same denominator. It's not possible to not get the same denominator. But wait a minute, sometimes my answer might be 2/3, 3/4. Yeah, that's because you reduced your fractions. What if I have a fraction followed by an integer? That's because you reduced them. But I just proved you always get the same denominator. It might reduce. Now, this is a lot of work to get to here. They kind of look like something. If I said consider the matrix, called matrix A, okay, A, B, C, D, and I want the determinant of A, isn't that minus that, the determinant? Mm-hmm. Look at my numerators and denominators. Don't they have the basic form of a determinant?
Yeah. Weird. Oh.
Yeah. In fact, both denominators are the same. Yes. Huh. If I said, I think these are determinants, well then x would be A, B, C, D, wouldn't it?
Yes.
Huh. And y would be the same denominator. Oops. A, B, C, D. You see it?
Mm-hmm.
So what would the numerator, what would it have to been? Now remember, I put all these letters in alphabetical order already. Look where they stand here. How can I get A, F, C, E unless I did
AC.
A, F,
and
that work?
Yeah, that would work.
And how about over here? I need DE minus BF. I need DE minus BF. Will that work?
Yeah. There we go.
So how did I know to put them in that position? By the way, sometimes this is easier if you have 3 and 4 and 5 equations. Well,
X1 and X2.
if I look at the coefficients only, that's the denominator, isn't it? I want the X solution. So if I replace the X numbers, I'm sorry, I said that badly. I want the, oh, you know what, I wrote that backwards. You guys are supposed, that's the Y solution, isn't it?
Mm-hmm.
Sorry, that's the Y solution. Again, I'm looking sideways. Yikes. So if I want the X solution, I replace the X coefficients with these, which is exactly what that is. If I want the Y solution, I replace the Y coefficients with these. Now, the funny thing is, regardless of the nature of the answer, I get 2 really happy integers. I get 2 hideous fractions. The amount of work required is exactly the same regardless of the level of the solution, by the way. It's always exactly the same. So I maintain actually the fastest way to solve 2 variables is this. I mean, you can give me any problem that exists and I'll get the total answer significantly under a minute. I mean, I can't even imagine this would take a whole minute because it's number, you're done. Even when the numbers are ugly. Now, what's this called? You guys remember? This is called Cramer's rule. Why am I showing you that? Because this is how we're going to solve every problem we do today at some point. This is going to come in. And when we're solving systems, this will be by far the easiest. It'll be by far the fastest way to solve it. It's not the only way. Is Cramer's rule efficient when you have more than 2 equations? No, it's terrible. No, you would never choose it. I got 4 variables, 4 equations. Let me do some 4x4 determinants. I'd have to do 5 of them, by the way. No. But if I'm doing 2 variables and 2 equations, this is light speed, but it's also the simplest way to do what we're going to do today. So I wanted to remind you what Cramer's rule was because we're going to use it today. And you go, oh, okay, cool. It's a very fast way to solve something.
I see how you got the Y where the AC and the EF came from. Where did for X, with that determinant, where did you get, for X?
Notice where I made the change. The Y, I replaced the Y coefficients with that. And for X, I replaced the X coefficients.
You're solving
And
for X.
If I had a 3x3, now you'd have an X, Y, and a Z, you do the same thing. You keep going. Now, obviously, if this is a bigger problem, you probably don't want to do this by hand. That's not the point. This is a beautiful technique. And by the way, I did this with numbers. Do these have to be numbers?
No.
No, you can take a determinant. A matrix can have scalars or scalar valued functions. A matrix can't have other matrices in it. It can't have vectors in it. But a matrix can have scalars or scalar valued functions. We're actually going to be dealing with functions as opposed to scalars. So the technique, the reason I like Cramer's rule is not only it's short, sweet, and fast, but I can't use a matrix efficiently to solve a system of equations that it doesn't have numbers. If I have a system of equations that's all functions, that's a kind of a tough thing to do with a matrix, isn't it? How do you do row operations? How do you eliminate things because they're functions? So this works beautifully. So now let's start the process. So here's. Let me see. Let me go the basic form I want. I want to use the same form. Now, before I was giving you coefficients, and you were going ahead and doing stuff, But let's suppose we just made the lead coefficient a 1 automatically. Okay. So I wanted to go in this form right off the bat. The P and the Q do not necessarily have to be constants. What we did before was, if you remember, I said A2 of X, A1 of X, A0 of X. Imagine now you just divide it through by A2 to make the lead coefficient a 1, just to make it cleaner. So now this is your new thing. These do not have to be scalars. These can be functions. And this whole thing equals some function. Now, if it turns out that the P and the Q are scalars, then I can use what we did before, right? I can do the auxiliary equation, find out my homogeneous solution really simply. Life is good. But it turns out we're going to learn several other techniques where these don't necessarily have to be scalars. They can actually be like x to a power. And I can solve that problem, the homogeneous problem. So now we're looking at the non-homogeneous. Last day when we did the method of undetermined coefficients, we had a couple rules. These guys had to be scalars in front, and tell me about the right side.
Had to be one of the four.
Yeah, we call it the big four. Sine, cosine, e, polynomial. What we're going to learn today works no matter what it is. It can still be one of those, but it can also be natural log. It can be tangent. Right? It can be something other than one of those guys, but it requires a little bit more. Now, if you remember when we did this substitution, let y2 equal u times y1. Remember, we said we knew y1, we said let it be this. You say, how can I say that? How could I even know that? Well, really what I'm saying is u equals y2 over y1. Oh, and y1 and y2 are existing. I'm just calling them u, but I don't know what u is yet. This is not anything that's complicated conceptually. We're going to do something very similar. So here what we're going to do is we found, okay, that's blue. Seems every time I pull a blue one out, it comes out green. We already know the homogeneous solution. Let's say we know that y1 and y2 are solutions to the homogeneous equation, okay? Everybody okay with that? So this is what we did last day. We found the solution to the homogeneous equation, and then we used the method of undetermined coefficients to figure out the particular. So let's assume that we found the solutions to the homogeneous, okay? Now, with that said, I'm going to define a new function. This is our final answer. Y is going to equal u1 times y1 plus u2 times y2. I don't know what u1 and u2 are yet. We're going to figure it out. But I absolutely can guarantee you that I can find this. In much the same way the one we just did. I said, you know, let y2 equal u times y1. We know it exists. We can find it.
So this is the assumed general solution that we will follow from now on? Or is...
Well, no, this will be to get the solution to the non-homogeneous.
So that's the particular.
So this will give me everything. Because you see the y1 and the y2 are already going to be in the answer. Do you remember when we did the reduction of order all the way to the end and we got both answers in there at the very end? This is going to have the same feel. We're going to get both answers in there at the end. We're going to get the y1, y2, and the particular all at the same time. But we're not going to segregate them. We're not going to say, oh, here's homogeneous, here's particular. We're going to have the entire solution in front of us, and you're going to say, oh, well, there's y1, there's y2, oh, there's a third function right there. The third function can be more than one term. And we're going to find it this way, okay? So now we're going to go through the process. The only assumption we're going to make is that we were actually able to solve the homogeneous, which is a fair assumption because that's all we've been working on lately. So we want to take the derivatives of this and then substitute it back in, okay? So let's do both derivatives, first and second. It's going to be kind of messy. So dy dx, and hold on a sec. I want to write it in this form, but I want to differentiate this. It is implied that u1, u2, y1, and y2 are all functions of x. Yes, you can write y1 of x. That's correct. We're lazy though, right? It's implied product rule. Like we did before, rather than write first times derivative of second plus second times derivative of first, it might be prudent to keep everything in the same order throughout. It's easier to gather terms and cancel terms. You guys remember this from remedial algebra. You were multiplying two polynomials together and you had an xy term and then somewhere else you had a yx term. Do you remember doing that? And no one recognized that they were the same terms? And I'd always say, always write them in alphabetical order, that way you don't miss them. Or you had worse. And the algebra students all said, well, those are the same term. Well, no, they're not, are they? But if I write my variables in alphabetical order, sometimes it's easier. Well, it's the same thing. It's just bookkeeping. But it's a strong suggestion. You're less likely to make errors. So first times derivative of the second plus the second times the derivative of the first. And then okay, there's my first derivative. And now I gotta do the same thing again. Yee. No shortcut, but we do know some things may end up doubling. That usually is what happens, right? So first times derivative of second plus second times derivative of first, okay? First times derivative of second, isn't that going to be exactly the same term?
Yeah.
So can I be lazy and just do a 2 there? Everybody see what I just did? I'm going to get the same term, and then derivative of first times the second. Because that term came up on that side and it came up on that side. Okay, we are lazy by nature. If you're a good math student, you have to be inherently lazy. Lazy doesn't mean you don't do things. No, it means you take shortcuts. You are efficient. Isn't the right side going to look exactly the same as the left side? With a 2 in the middle? So can I just write the right side?
Yeah.
Yeah, I'm lazy. This gives me this, so this ought to look real similar. Just get the 1s and 2s correct. So u2 d squared y2 dx plus 2 du2 dx dy2 dx. And then the last one would be d squared u2 dx squared y2. Okay? Now I got to substitute it all in. A lot of stuff's going to disappear. Why? Because we know y1 and y2 are solutions of the homogeneous. That's going to fit in there somewhere. If I rewrote this, and I put a 1, and a 1 right there, wouldn't that equal 0? If I did the same thing with 2, 2, 2, because we just said those are the solutions to the homogeneous. So that's going to show up in some capacity. I'll do it under here, because I'm going to need the space.
For the du, is it du dx or du dy?
No, everything's a function of x.
Okay.
Are my x's ugly?
Okay.
No,
thought
they're
I saw
very
that
pretty.
Oh,
top
this
one.
should be square.
I saw that
On the top
one.
one, it looks like a Y.
Yeah.
Which one are you talking?
The
Top
second
row?
one.
Yeah.
Second one on the top.
Oh yeah. dy dx. The second one. The second.
Oh,
one, yeah.
just, yeah.
Okay.
I'm sloppy, okay. I can blame it on all sorts of things, but I won't. I'll save that for later whenever I really need to blame it on something. I was just curious. I really do need you guys to sometimes catch those things. It drives me crazy. I'm doing a lecture and then someone said, oh yeah, way back when it was supposed to be this. Like, why do you wait till the end of class to tell me? You know, everyone's confused. Yeah, that's what it's supposed to look like. Now let's substitute it in, as ugly as it is. So we have u1 d squared y1 dx squared plus 2. This is why you started the problem by getting rid of the lead coefficient, by the way, because that would be even worse at this point. Hold on, did I? Oh, here we go, right here. D squared u1 dx squared y1. Oof. By the way, if you don't want to take detailed notes right now, I have all the notes, the derivation of this is on the notes section online. So if you want to just follow along, I probably should have had you print them. I didn't even think of that. I'm a big fan of print them and then write all over them. But a lot of you can tell me what the next thing is. This is one of the reasons why note taking is so critical. Because if you know what's going on, you're already ahead of me. You've already started filling things in.
Did you say this was Cauchy-Euler or?
No, this is variation parameters. That's what this one is. Okay, where are we now? Now we're doing p of x times the first derivative. And let's see, how do I want to write that? I'm going to do that as, hold on. Yeah, there's really no shortcut. I'll just write it out. So I'm going to write it like this because I'm going to gather terms in a minute. Okay. Now, what we're gonna do is, we're gonna rearrange and gather terms. But the way I'm gonna gather terms is, I want every term that has a U1 in it first. So, let me get my... Does that look like it? That's every term with a U1. Yes, no, maybe? Okay, let's rewrite it with the U1 factored out. So all of this is equal to, I'll put it up here, U1 times you're gonna like this part here a lot.
Does it all go magically away?
Yep. I don't know, I'd say magically. By the way, isn't that 0? Now, all the terms with a U2 in them. I think you've seen this movie before, haven't you? Let's see. It's going to look exactly the same, but now with Y2. And again, that's 0. So how much of this have we gotten rid of? A lot, not all of it. So we still have that, a little of that. We still have some stuff left. Agreed? And let's see. I'm going to be lazy. I'm just going to underline what we have left rather than rewrite it. Yeah.
Why did you say that was 0?
Because y1 and y2 are solutions to the homogeneous equation. So that's what I was saying earlier. If I take that equation and I stick y1 or y2 in there, it's got to be 0 on the left because they are solutions to the homogeneous. That's why that's 0. Because I just stuck y1 and y2 in there. So what's left? Let me underline everything that's left because I don't really feel like rewriting it all. I had to write it so we could gather. Is that it? I think that is, okay, so I have
Oh,
one.
there's one more.
Is there one
It's
more?
right on the metal part,
Oh, yeah.
on the other side of the U2.
Oh, thank you, this one here. Good. These are the terms we have left. So what I'm gonna do is I need to erase. I hate doing that, but I need a lot of room here. So we all know this stuff here. Now, here's where it gets a little bit tricky, and it almost feels like we're cheating in some sense. We're going to create a system of equations in a moment. So right now, let's see, which terms do we have? We have, if I take those terms and gather them, okay, where is it? What is this? Exactly, what are this term? Let me go. So hold on, D1, U1. So I have this term and this term. I think that's, yeah, that's what I have, those two terms right there. Right there. I'm gonna write it over here. I didn't mess that up too badly. I have d dx of y1 du1 dx. And then I have d dx of y2 du2 dx. Look at the second derivative terms primarily. Okay? So you can clearly see that's the second one, and then that's one of the first ones. I used one of these, and I used this. Boom. I used, where are we? One of these, and I used this. Boom. Can everybody see that?
Oh.
If I just think product rule, okay? Now, what else do I have? But then I also have the P of X times this guy. I like this. I have to do this because I never find everything if I just leave it up here. That's U1. And then plus y2. Okay, that is taking that plus that. Remember, I didn't even, right? I didn't do anything to them. Now I said we used one of this one and we used one of this one, so I still have one of each of those left. And so that's the last thing I'm going to write. I'm going to write all of this and then plus a single du1 dx, dy1 dx, plus du2 dx, plus dy2 dx. It seems kind of wonky, but now everything I have on the right has now been accounted for. Some of it's 0. The rest of everything I have on the right is right here. Okay, so far so good?
Question.
Yes.
The stuff on the bottom there is, you're saying is.
It's all of this is being added. This,
Yeah, but where you got those is from here,
Oh.
but you didn't use it, right? Yeah.
one of these, when I do this first times derivative of second, second times derivative of first, I only get one of them, and then this is the other one. Same thing here, that's the other one. This is by design. Again, I'd like to take credit for this theory and development. No, I just do it.
Why don't you rewrite it the same way you wrote the first one? Because you see the d dx y1, because you said that.
Well, because this one still has a y1 in it.
Doesn't that
This one won't have a y1. So when I do first times derivative of second, that's what this term is right here.
Oh.
y1 times the second derivative.
Oh, okay.
But then when I do second times derivative of first, I get this term
Okay.
one time, and then I get this term a second time. That's why I put, but this is out of convenience.
All of this still equals f of x, right?
All of this now equals just f of
Okay,
x.
great.
I hate to do this too, but I'm gonna need to erase the right side at some point. Yeah.
I missed it. So why did those equations equal 0?
Okay, anybody want to handle that one? I've answered that a couple times. See if you guys are paying attention. They are solutions to the homogeneous, therefore, if I substitute them in, by the way, if I substitute something that wasn't a solution to the homogeneous, it wouldn't equal it. That's why it's so important that I said we started by saying we're assuming we know y1 and y2. We will. We'll find those before we do anything else. Yeah, Patrick.
Where did that U1 and U2 go from that big
Those were that's the red underline was what I pulled apart, and that's 0. So we got rid of half of this problem right off the bat. Half of it was 0. This is what's left, and I rewrote it in sort of a different form. You guys with me on that? So we know that this is all that's left, and this plus this plus this plus this all equals f of x. Yikes.
I just wanted, you put an extra plus sign at the end. It should be du2 over dx times dy2 over dx. Like literally the last term, right before the equals after that.
Thank you. That's a times. Good catch.
Just to clarify, that second d over dx is to that other 2? No.
Yeah, one of them came from here, and the second one was here. And then we did the same thing. One of them came from here, and the second one came from here.
Okay.
This is, again, this is unbelievably brilliant and clever at the same time, whoever figured this out. I don't know what went into the thinking, you know, but I think the person's name was Professor Parameter, but I'm not sure, you know. That's a joke. It's variation of parameters. This is what this is called. Okay, now that I got that, let me get rid of, I think I can get rid of this stuff here. I don't like doing that, but we need the space. So now I gotta solve a bunch of stuff here. But the stuff I'm about to solve is not gonna be that bad. Now, this is why I say we're gonna make a couple of assumptions that are not unreasonable, but are gonna seem kind of weird at first. Okay? I need to do something here. So what I'm going to do is I'm going to consider two different sets of equations. Okay? I'm going to consider two different sets of equations. This is one of them right here. Okay. Now, if I'm saying I'm going to set this part here equal to f of x, what does that mean about the rest of it?
It equals 0.
It would have to equal 0.
Well, doesn't the p go to 0? Oh, wait.
No, p is fine. P is not a problem. The rest of this would have to equal 0. Actually, I only need this to equal 0. Why? Because now I'm multiplying it by p, it's still 0. Now I'm differentiating the sum. I'm differentiating 0. This is why this is so brilliant. Now, hold on, I wrote these in reverse. I need to, hold on, what order do I want to write these in? I want the y ones, oh, you know what? I'm gonna put the y ones first, because I need things in the same order. Sorry.
Why exactly should you say that that's equal to f?
I'm gonna show you that in a moment. I want the y to be first, because it's first in those equations there. And now I have y1 plus y2, that's a u, so that, okay. There are an infinite number of different systems of equations I could create. And every one of them would give me a different version of the u1 and u2 that would satisfy that particular one. But in the end, I'm still going to get the same final answer. This sounds kind of wonky. There's an infinite number of u1s and u2s that would solve this equation. There's an infinite number that would solve this equation, but there's only one pair that will solve both at the same time. Put a number here just for fun, but put a 3. Well, now there's a different set that will solve that one. But any u1 and u2 that solves them simultaneously will always be the same ones. This is kind of crazy. We've done versions of this before. If I set up the system, whatever u1 and u2 aren't my final answers. It's y1 times u1 plus y2 times u2 gets me to my final answer. That's good. Think of that as literally as one function. And so if I said I'm going to solve this version, every version of the second equation will give me the same final answer. This is just the easiest version. By setting that equal to f, then everything else had to be 0. But like I said, I only need this part to be 0 because now I'm multiplying by a function and now I'm differentiating the sum. Remember, the sum of the derivatives is the derivative of the sum. That's what I'm saying. This is just brilliant. So now I need to solve this system of equations. Man, that looks scary. Well, actually, I only have 2 unknowns. Remember, we know what y1 and y2 are. Those are our solutions to the homogeneous.
Is it just the nature of trying to find u1 and y1, u2, y2, and multiplying them to get y? Is that why we're able to just set the top equation equal to f of x? Or
more or less, there's an infinite number of variations I could do, and I'll always get the same y function at the end. I will not get the same u1 and u2. Again, think of it this way. Let's just say for fun, y was sine x, we'll keep it simple, and y2 was cos x. But my final answer had something completely different. Even for fun, what if my final answer didn't even have sine and cosine in it? It's because the u1 and u2 would have sines and cosines in their denominators. You with me on that? Okay, so what if I said, let's call y1 some linear combination of these? Then my u2, 1, u2 would be different functions. Whatever I'm calling y1 and y2, my u1 and u2 are not unique. It's just when I do y1 times u1, y2 times u2, together they will give me the same answer. But there's an infinite number of variations. Let's say the final answer, I'll keep it simple here. Let's say the final answer is c1 sine plus c2 cos plus, I don't know, e to the x. Okay, what if I make my u1 1 plus, how about 1 plus e to the negative x, and then I make my u2 1 plus, so what could I do to make that all come back now? E to the x over cosine of x minus e to the negative x. There, I think that'll work. I'm just making it up as I go. So if I multiply this by cosine, I'm going to get an e to the x minus e to the negative x. And here I'm going to get the sine. I should do one more thing. And then, minus sine. There we go. There. Now when I multiply by cosine, everything will cancel beautifully and I'll get my answer. I'm being silly. Let's make up a different u1. Make up any function you want. And now I will be able to tell you a u2 that will make this work. There's an infinite number of things I can write here, and every one of them will have a matching partner here. that when I'm done applying everything, U1 and U2 are not unique. There's an infinite number of possible U1s and U2s that will always get me to the final answer. They work in pairs. Does that make sense? I'm not looking for a unique U1 and U2, so I'm making my life easier by looking for the U1 and U2 that will solve this system, because this system does solve this problem. If I just said, let's, just for fun, let's call this, -3, then this would be 3, wouldn't it? Or something like that. No, I don't want to do that one. This one's easier. Now, tell me about this system. I know Y1 and Y2, they are not unknowns. What are the unknowns? How the heck am I supposed to find du1 dx? I don't know. Kramer's rule. I need more space, obviously. But yeah, it's Kramer's rule. And then du2 dx. Okay, so we did it before, but my coefficients are not scalars, are they? My coefficients are actually the functions themselves. Oh, by the way, does it matter which one's first and which one's second? Yeah, we usually do this one as the first one. Just so you know, we usually do this as the first equation and that one is the second equation. I'll show you why in a moment. So let's think of this one as being on top.
Are you saying because it's homogeneous that we use that as the first equation, or is it?
No, actually there's a simpler, let me put up top, there's a simpler reason that is not apparent yet. Let me put this up here. You're always going to want to do this one first, and I'll show you why in just a moment. By the way, does it matter what order I do them in terms of solving the problem? No. But there's something about the nature of the solution. I'm going to put that one on top. So now put down your coefficients. Won't it be y1 dy1 dx? I'm sorry, that's on the bottom, my bad. Sorry. y1 dy1 dx. And this will be what? y2 dy2 dx. And then here it will be 0 f of x. And on this side it'll be y2 dy2 dx. Everybody cool with that? Because that's the first one. Yeah. Same denominator. And we're going to actually give these guys names. These are white. Oh no, shoot, I had it right first time. y1. My fingers are the worst eraser, aren't they? Oh, that didn't help much. dy1 dx. This is dy2 dx. And now this column becomes the, see, this is the opposite side. Sorry, this should be, this is so we're doing, sorry, which one are we doing here?
Right side.
We're doing that side. Okay, so therefore what goes here?
y1 dy1 of x. Oh, that side.
Yeah, so that's where those guys go, and then this would be the y1. This is why I reviewed Kramer's rule really quickly so you know where everything goes. Can this be ugly? Yeah, it can be.
Well, we can jump straight to that part, right?
Well, no, you've actually got to start. You got to set up. Yeah, you got to set it up first. But all the derivation I did to get to here. So we'll do some examples, and I'll show you where. Yes, I do want you to skip certain things. Please, before you guys leave today, you're going to go quickly invent a combustion engine and invent the wheel while you're at it, so you can have to. Yeah, but sometimes we do that every day, right? We invent a car so we can drive home. No, there's certain things you get to take. Let me finish the minute though. Yeah,
we moved our y1 and y2
to the top
just for formatting.
Yeah.
Right.
Why?
Wronskian?
Because the denominators are the Wronskian. That's why. I promised you it was coming. I said the Wronskian is going to be part of our answer. Does everybody catch that?
Well, yeah.
Function derivative.
Yeah.
Function derivative. The denominators are the Wronskian of the linearly independent solutions. That's why I said let's do it in this order. There's less thought now required on your part. It would not change the final answer at all. But now knowing the denominator is the Wronskian, you can fast forward certain things. And I'm going to show you everywhere you can fast forward, because this is not a short problem, well, so far. Isn't that beautiful? The bottoms of the Wronskian. This is why we went over the Wronskian, because I said it would come up. I'm never gonna ask you to use the Wronskian to determine if something's linearly independent or not. You're finding your solutions, you're probably not messing them up. But the Wronskian actually is making its way into the final answer of this problem. Interesting. Now, I find this, I'm going to get probably a very simple function in the end. But that's the derivative, isn't it? So that means I have to integrate. I have not done any calculus yet, really. I'm gonna have to integrate to get the U1 and the U2. Then I can tell you the final answer, and that's actually the easiest part of the problem. So we'll do one in a minute.
So just to repeat, you're saying that we need the denominator to be the Wronskian in order for this. to
It's,
work.
well, if I recognize the denominator is Wronskian, then probably on the right path.
Okay, but we can just rearrange our system
Yeah,
just
but,
to
but
make
then you're gonna get the
product.
negative, and that's not wrong.
Yeah.
Everything's changed, you can have a negative numerator, negative denominator, they'd cancel. So now, I've got all this going, assuming I can solve this, I can then finish the problem. We'll do an example in a moment, okay? I need to label these things. So what I like doing, when I'm doing Cramer's rule, and I'm doing this in baby algebra, because I do Cramer's rule in linear algebra, some of you were in my class, and I do it in baby algebra, and I do it the exact same way. When I've got this problem here, let's just make up a simple one, you know. I have 3 determinants. And this part is actually quite important. It's labeling them so I don't get lost in the process. So this is one for the x, and this is the one for the y. So what I do is I call this big D, D for the determinant of the coefficient matrix. Then I just call this one dx, and I call this one dy, and then x equals dx over d, y equals dy over d. It makes it just so much easier for the bookkeeping. Now I calculate each of these, I tell you the answer, and my answer is hideous fractions, but I did no work whatsoever with any fractions, only my answer. So what the kind of universal thing is, we'll call this guy, how about, I don't know, W. You like that? But what should I call the top one? How about W?
U1.
Or just W1? We're lazy, we're math people. How about this one? I don't know. You like that? I gotta get it right. I need my bookkeeping to work, but keep it as simple. Since the bottom is the Wronskian, I'm just calling it W. But the top is a version that I've altered by changing a column, but it's also not just that. I gotta make sure I'm associating it with the correct variable. That's actually really critical. Yeah, you can call it sub U1. I think the textbook actually does that way. I'm lazier than I just say sub 1. I think in the book they do sub U1. I think on my notes, yeah, I just did sub 1. Okay, so, we'll do an example.
Just for clarification, the function, or it's not even the function, the equation that equals 0 is always going to be the one on top, just for like the bookkeeping purposes.
It's easier, yeah.
Yeah.
Yeah, so let's do something from beginning to end. It's much easier to track things. When I derived the reduction of order, there was a lot of stuff going on. There was a lot of algebra, and the final result looked so scary because it was abstract. Then every time you did a reduction order, you realized there was a lot less stuff to write down, wasn't there? Everything combined and canceled. And you always got something ridiculously simple, and that's the nature of the beast. This is really going to be the same thing. It's going to be really simple in the end. So, let's do a problem, first of all, let's do one that's actually easy. Let me start with an easy problem. How about we do one that we wouldn't actually need variation parameters for. I want to make it really simple. All right, so minus 2 dy dx minus 8y, and let's say that equals e to the, I don't know, 3x. We would use method of undetermined coefficients on this one. Agreed? But I want to use variation parameters so you can see the process. If this was an exam question and I said solve, you solve it. You would probably opt for undetermined coefficients because it's a lot less work. But the function on the right, if it were different, when the next example would be different, then you'd have to do variation. So I want you to understand how that one works. So let's start with this part. So m minus 4, m plus 2. So the solutions to my auxiliary equation are 4 or negative 2? So y1 is what?
E to the 4x
And y2 is?
to the negative.
Everybody cool with that? So now I start the problem. Y equals u1 e to the 4x plus u2 e to the negative 2x.
Starting equation equals e to the 3x, right?
Yes.
Okay, sorry to see.
Can you not see it from here? Sorry. So we just solved the homogeneous. And I'm saying now the solution, the overall solution is going to look like that. But wait a minute, shouldn't there be another function? The u1 and u2 will have just enough stuff that when I multiply it out, you're going to see the emergence of another one. It's hard to explain until you actually do it. I'm choosing one that's simpler than we would actually have to do just so the algebra is easy. Now, this statement here is kind of critical. So now the question, can we go to this statement now? Yes, that was the entire point of the last half hour, was to get to this. Everybody okay with that? But you know what y1 and y2 are. They're not variables that are going to show up in an expression. They're the actual functions themselves. So tell me, what are my two equations that I'm now going to solve? I erased everything.
du1 over dx equals.
So no, you want to state these before you do this, because
Okay.
you got to know what it. This doesn't mean anything if I don't have equations. So it's going to be what?
dy
y1.
Oh,
Well, what's y1?
E to the 4x.
E to the 4x du1 dx
plus negative 2x. Yeah.
plus e to the negative 2x
du.
du2 dx equals 0. And then what's the next one I'm going to solve?
The derivative for
So-
e to the 4x du1 minus 2 e to the equals e to the 3x.
You should like that we can write this as the next thing. We haven't really, have we done any work? Well, we factored a quadratic. I guess we put in a hard day's work. We factored a quadratic. That's basically all we did today. All right, so now, you can't use Cramer's rule to solve a system of equations unless you have a system of equations, yeah. You got to have something to actually solve, but you didn't have to do any work. But now you can say, don't write the quotient, actually write W, W1, and W2 as 3 independent statements. I don't want to do that, it's too messy. Do each one separately, it's easier. So, my Wronskian is e to the 4x, 4e to the 4x, e to the negative 2x, negative 2e to the negative 2x, and what does that equal?
Negative 2e to the 2x minus 4e to the 2x.
So negative 6, everybody agree with that? My Wronskian is equal to that. W1, which would be the numerator, so that's, I'm going to replace this column with those guys. So 0 e to the 3x. And when I do it in baby algebra, I always do it the same way. I always stack these. By the way, it's more obvious if it's a 3 by 3 or bigger. I stack these, and now I'm going to first change the x column, then I'm going to change the y column. If it were 3 by 3, I would then change the z column. But I'm always going back to here to figure out the new things. It's just so much easier. In the long run, I guarantee you, I always do less than everyone else. I'm the laziest person around. I know how to be efficient, and I know how to completely avoid certain types of errors. By stacking them, you are far less likely to put something in the wrong place, which is the number one error. Your error is not going to be a calculus error. It's going to be putting things in the wrong place. So I'm doing this one 3 times, but over here I'm now changing that guy. So that gets repeated there. This is Cramer's rule. That gets repeated there. That's it. The evaluation of the determinants will not trouble you. I don't care how complicated the functions are. Evaluating the determinants is easy. Integrating the result may or may not be a challenge, depending on what your functions look like. So what is this? 0 minus,
E to the x.
and this one is
0
Careful.
Oh,
to-
yeah, e to the 7x.
E to the 7x minus 0. I can now say with certainty, du1 dx is equal to what? This over that. Everybody cool with that? And what is that? That's positive 1/6 e to the negative x. So far, so good? So this over this. All right. U1 equals, so it's the integral of this guy. And what would that be?
Negative 1/6.
Negative 1/6. The C1 is kind of important. It really is kind of important in this case. And what's the U2? Integral of negative 1/6 e to the 5x. If I didn't mess this up totally, I don't think we messed this up totally.
Negative
did we?
1/30th?
I don't think we messed it up. So it's, sorry. Negative 1/30th e to the 5x plus c2. So far, so good? We have one more step in the problem. Now we're going to do that. You're going to like this. Is any step so far terribly challenging, you think? So far? No, if there's any challenge in the entire problem, if there's any, it's going to come right here. These functions may be more challenging to integrate. At the absolute worst, and this is where this is going to happen the most in this entire course, I may have to do an integration by parts. You have no control over that. Let me throw a what if at you. What if my homogeneous solutions were sines and cosines and I have the e? You're integrating sines and cosines times e. No way around it. You're going to do something, yucky. It is what it is. All right, so what does y equal? What was y1 was e to the 4x. So it's negative a sixth e to the negative x plus c1 times e to the 4x plus negative 1/30th. Is that right?
Yep.
Make sure I'm reading that correctly. E to the what?
Negative 2x.
All right, let's distribute. I'd have negative a sixth e to the 3x plus c1 e to the 4x minus 1/30th e to the 3x plus c2 e to the negative 2x. How about if I rewrite that as c1 e to the 4x plus c2 e to the negative 2x? What is negative a sixth plus negative a 30th?
6/30ths.
Yes. It would be negative 1/5.
Yeah.
And there's my final answer. What did I say? I said when all is said and done, the YP is going to fall into your lap. Look in your lap. Does everybody see a YP in your lap?
Yeah.
Figuratively speaking, yeah. And by the way, do you see the homogeneous just perfectly? Yeah. This one works out so beautifully. You didn't have to be clever. You just don't forget the C1 and the C2. By the way, if we had done this using the method of undetermined coefficients, didn't we know our answer was going to be a multiple e to the 3x? Didn't we already know that? Yeah, that's why I chose this example, because this was overly easy. Kind of cool, huh? But I could have done this using undetermined coefficients, and you're absolutely correct. You should have done this if this was a test question. You'd have been done a long time ago. But now that you see the process, now we're going to do it to one that you can't use undetermined coefficients for. Okay? Let's take something mean and cruel. Let's see. Here's a good one. By the way, you don't like the secret to the 3x. Actually, you should. Because your homogeneous solutions are going to be sine and cosine of 3x. Yeah. Does everybody see that your homogeneous is gonna be sine cosine of 3x? You want that to be 3x, because imagine when you're doing derivatives and combining terms, if you had different arguments, that would be difficult. Yeah, so you're going, oh, that is no, you don't want to wonder. You'd really like the argument to all your trig terms to be the same if humanly possible, and that is probably more likely. All right, so let's solve the homogeneous first. M squared plus 9 equals 0, so m is plus or minus 3i. So y1 is cosine 3x, y2 is sine 3x. You're never going to be fast at this, but you can be very efficient, because you only have to do a few problems to start seeing, you know, the nature of things and what order you should do things. So first declaration is that y equals. Better, hold on. I think what did I write? I wrote u1 y1 plus. That might seem redundant, but how the heck am I going to get that unless I have that statement? I don't know what I'm supposed to put together at the end. I need to state that at the beginning to give me my instruction for the end of the problem. I don't need you to take two derivatives, substitute them back in, let everything cancel, gather terms. No, I did that already generically. We already now know how to go directly to my system, but you need the system because Cramer's rule is solving the system. So my system is what? y1 plus y2, where's that stuff over here? In certain situations, I really like this method. If the functions are really ugly, I'm not a big fan. Yeah, John?
Do you not need to write, or just, I'm not sure if the u1, y1 plus u2, y2 replaces what we normally wrote, where it was like y equals c1 cosine 3x.
No. I don't have the arbitrary constants yet. These are my two linearly independent solutions. At the end of the problem, I'm going to see a c1 cos plus c2 sine plus yp. Remember, that's what you did last day. You said you found these first, then your homogeneous solution was c1 of these plus c2 of these. That's correct. And you used the method of undetermined coefficients to find the yp. And that's exactly what you should do if that's one of the big four. But it's not. So therefore, I can't do it that way. So I'm going to leave these alone because they are going to show up at the end of the problem anyway. Okay. The C1 and C2 will magically appear when I do my two integrations. So the arbitrary constants that showed up in my integrations, they will be the same C1 and C2. That's one of the beautiful things about this method. So that's equal to what?
0.
Now the derivative, so negative 3 sine 3x du1 dx
Plus 3 cosine.
plus 3 cosine 3x du2. You're going to like this one a lot, I'm just saying.
Oh yeah. That equals 1.
One thing about a Wronskian, we're not concerned with Wronskians, they're usually nice, but you really, really like Wronskians with trig. Because the only trig you ever get that are homogeneous are going to be sines and cosines. All right, let's go out on a limb here. My Wronskian is, let's see, cosine 3x and then its derivative, sine 3x and its derivative. I'll just go ahead and evaluate as I go. It's probably just as easy. All right, so let's see. That's going to be what? 3 cos squared of 3x minus negative 3 sine squared of 3x. That's
3, right?
3.
Yeah.
No. Like I said, you love sines and cosines here because you're always going to get a constant for your Wronskian when you have sine and cosine. Always. No exception. Why? How do I know that? Because you have to get the same argument. So it's always going to be a cos squared theta plus sine squared theta. If theta has a chain rule factor, okay, it did. 3. Don't memorize that as a formula. Just do that. It's pretty simple. Now, W1, we have this. What goes here? 0 minus. Oh gosh, what's sine times secant? Oh gosh, that's so tough.
Tangent.
10. This is gonna be very friendly.
Is it my negative tangent?
Yes, thank you, negative tangent. Good catch. And then this one is gonna be cosine 3x, negative 3 sine 3x, and 0 secant. All right, oh, this is gonna, oh, cosine times secant.
It's the most obscure trig identity.
Oh, what's cosine times secant? Well, according to our group, on the last test, the reciprocal of cosecant was cosine, so obviously these don't go together. No, they kind of go together really well, don't they? I'm gonna get a 1/3 for one of these guys, aren't I?
Yeah.
That's kind of nice. I like that. Okay. So let's now state, we can't state U1 and U2 yet, we can state the derivatives. So du1 dx is that over that, so how about if I just write negative 1/3 tangent of 3x, and du2 dx is gonna be 1/3. Wow. I like that. Okay, now go slow. This is the only real calculus in the problem that we're doing. We got to integrate, so we want to make sure we get it right. So u1 is the integral of negative 1/3 tangent of 3x dx. Well, the integral of tangent involves a log secant, but this is a negative tangent, so I can say log of cosine. Generally speaking, this is one of those strange things. A lot of folks don't realize this. You had a calculus teacher that didn't help you, and they told you this was the answer. This is not the answer. Would any of you ever say the answer to the question is the negative of -1? Would you ever say that? No. This is always negative. You have the negative of a negative answer. You don't ever answer a question the negative of a negative answer. This is log of secant. And the funny thing is the check, the derivative of secant is secant tangent divided by secant is tangent. The derivative of this, and now I got to do some algebra, some work, probably going to cancel badly, probably not getting tangent back. No, but we have a negative in front. And a negative in front is the same as saying the log of the reciprocal. I would rather not have a negative coefficient in front of a logarithm if I can avoid it, So in this case, I would go with positive log cosine. Where is it? Right here. So positive 1/3 log, and I have to say absolute value of cosine because cosine could in fact be negative. And I'll call that C1. I just want to remind people, because most of you do that correctly, but in this case, by the way, would it be wrong to say negative log secant? Would that be wrong? Not at all. I'd just rather add the logs than subtract the logs. I think it's cleaner.
Cosine 3x, right?
Oh yeah,
the
thank you.
1/3
Thank you.
The one that goes away, right, from chain rule? Yeah.
And the 1/3, you're right, it does, no,
Oh, wait,
it doesn't go away.
1/9.
1/9. Good catch, again. I'm the only one that can't see that. U2, what's U2? 1/3 dx? So is that just 0? No, it's,
1/3 x.
yeah, believe it or not, sometimes we forget we take the derivative instead of the antiderivative. That would be wrong. Okay, so my final answer, when all is said and done and I get to multiply everything out, y equals cos 3x times this, so I'm going to write it as C1 cos 3x plus 1/9 cos 3x log cos 3x, that's kind of ugly, plus, now I'm taking sine 3x times this, so I'm going to say plus C2 sine 3x plus 1/3 x sine 3x. And that's my answer. I am pretty sure I did this whole thing correctly. On a test, you probably have to go with pretty sure. You have time. How do you know?
Plug in your initial conditions.
Well, I don't have initial conditions, but what do you think?
How did you get that 1/9 cosine 3x.
Oh, because the chain rule factor, I would need a 3 because of the 3 there.
I get that.
Oh.
The log at the end. Like it's 1/9 cosine 3x log absolute value cosine.
Well, because I'm taking my cosine function and I'm multiplying it by the entire
Oh,
U1.
that's a C1.
This is U1.
Oh, okay, yeah, it's U1 times Y1. Okay.
Yeah. So how do I check? Well, first of all, either you checked or you just you observed the sine cosine are correct. I'll give you the benefit of the doubt. You observed that. So when I'm checking this answer, do I have to worry about the sine and cosine satisfying the homogeneous? No, you did that at the beginning. So when you're checking, what are you doing?
Check the particular.
Yeah, you got to take 2 derivatives of that, which,
I don't wanna.
well, as bad as it looks, it actually won't be as bad as you think. Because when I differentiate the log, won't I get a cosine in the denominator that's going to cancel that cosine?
Yeah.
This one actually will check okay. It's, I mean, not easy, but you can do this. You can do this, okay? So when all is said and done and everything cancels, I would hope that I'm left with that secant term. That's really the only thing you can do is to take 2 derivatives. But, you know, on an exam, you probably don't have that luxury, but when you're doing this on your own, you have a week to do it, yeah, you should probably check it.
We're used to writing our C1
Oh,
term followed by.
you can put, I would probably write them first. But remember, I distributed
Correct.
cosine times the first, and then I distributed sine times the
But it
second.
doesn't.
Do you think it makes any difference the order I write the term? No. In the previous problem where we only had one additional term, it was really easy to just make that the last term. If this were a solutions manual, I don't know if the author would automatically just move this over here. That's fine. Most of us would rather see it there because then it's a clear distinction between the homogeneous and the particular. But does it change anything? No. So whatever order you did it in, just make sure that you can clearly see the homogeneous in that final answer.
We wrote the integral of tangent as a log cosine because of that negative out front.
Yeah, it would have been absolutely correct to say negative log secant.
Yeah,
That would be
that's
absolutely
like
correct.
kind of the negative of a negative one.
But here's another thing. If I'm going to check this, what would I rather have there, a cosine or a secant? For the check. I'd probably rather a cosine because it's the derivative of this divided by this, which would then cancel with this. So do you see that there might be an advantage for the check? I will assume that you will choose to check something at some point. This is a beautiful method. If this is the question, this actually will be the only method I think that exists to solve this one. I don't think there is another one, not for this one. The first problem I did, we knew we could use undetermined coefficients. So what I like to do on an exam is I might give you that problem, but say use variation parameters, knowing it's a lot less taxing than this one. I might give you that last problem and say, and one of your solutions is this, use reduction of order. I will sometimes do that. I'll sometimes take a really easy problem that you already know and ask you to use a technique just so you can demonstrate you know the technique. And the reason it's so important, you all have linear algebra. So I give you a system of equations and I say, solve this system using Cramer's rule. And you go, well, it's so much easier to just use a matrix. I'm going to use a matrix. And then you got a 0. Why? Because you demonstrated you had no idea how to do the question. So if you're asked to do it a specific way, you got to use that because you're demonstrating your ability to do that technique. Most of the time, though, the instruction will be solve the problem. If this was an exam question, I would tell you to use variation of parameters. Why? Because that's the only way to solve it. I don't want you sitting there trialing and erroring other methods that aren't working. I'm just going to say, no, use variation of parameters because, hint, hint, that's the only way to do it. But I also might give you a really low-level problem that you don't need variation of parameters to do, like the first problem, and say use variation of parameters so you can demonstrate your ability to do it knowing you're going to get all really, simple stuff along the way. That's not unusual either, is it? So I might do that, but you will do a variation of parameters on the next exam. You're probably going to do a reduction of order, but again, it will be something a low enough level that you're not going to get lost in the algebra. Will there be integration by parts along the way? Sure. I mean, you can now see why there might be an integration by parts. When I'm doing this process, if my homogeneous solution is completely different than the function on the other side, I'm always going to have a parts. There's no way around it. What if my homogeneous was, you know, a couple of e to the x's. That would be particularly nasty, wouldn't it? E times sine and cosine is bad enough to integrate, but e times secant? Yeah, so that's why we tend not to dwell on that problem, but understand that problem does exist. Where are you going to see that problem most likely? I'll give you a hint. It's the Voldemort that we don't talk about, the P word.
Oh,
Quiz?
physics.
We shall not utter that name. Yeah, I can't tell you how many students I've had come to me with this, God, I asked to solve this problem in physics. Like, oh, that's the same one we avoided in DiffyQ. We avoided it just because it was too ugly, nasty, and took too long, but it is something that you actually can do, okay?